Astronomers thought they had seen everything when 3I Atta arrived, an interstellar comet that defied 12 fundamental rules of physics, with jets that refused to bend and a composition that matched nothing in our solar system. Then, on November 15th, 2025, something far more powerful locked onto it. Solar physicists at NASA's Goddard Space Flight Center watched their monitors in stunned silence as measurements flooded in from the sun's surface. A coronal mass ejection had just erupted with a magnetic payload 93 times stronger than any CME ever tracked toward an interstellar visitor. Within 6 hours, 3 independent tracking stations confirmed what seemed impossible. This 4.2 trillion kilogram wall of magnetized plasma was aimed directly at 3.1 Atlas, traveling at 2,800 kilometers per second. The comet that had already shattered our understanding of interstellar objects was about to face the solar system's most violent phenomenon. Impact was calculated for November 20th. What happened next would either destroy the comet or reveal what it truly was. Every space agency on Earth turned their instruments toward a single point in space. The countdown had begun. The monster emerges. Solar Dynamics Observatory's atmospheric imaging assembly captured the first frames of the eruption on November 15th, 2025. A massive magnetic filament, suspended in the sun's corona for nearly 2 weeks, suddenly destabilized. The collapse triggered an explosion of superheated plasma that punched through the sun's outer atmosphere at unprecedented speed. Within the first 30 minutes, the helioseismic and magnetic imager aboard SDO measured the CME's magnetic field strength at 4,800 nanoteslas, a value that immediately flagged automated alert systems across NASA's heliophysics division. Standard coronal mass ejections aimed at Earth typically measure between 20 and 100 nanoteslas. The largest CME on record, the September 1859 Carrington event, was estimated at roughly 1,700 nanoteslas based on ground magnetometer data and auroral observations. This new ejection was nearly 3 times stronger and still accelerating. The European Space Agency's solar orbiter, positioned 42 million kilometers from the Sun, captured the eruption from a lateral angle. Its extreme ultraviolet imager recorded the full 3-dimensional structure of the expanding plasma cloud. The data revealed a twisted, helical, magnetic topology, a rope-like configuration where multiple magnetic field lines wound around each other in a configuration plasma physicists call a flux rope. This particular rope measured approximately 380,000 kilometers in diameter, wider than Jupiter, and contained an estimated 4.2 trillion kilograms of ionized hydrogen and helium. The total kinetic energy, calculated from velocity and mass measurements, exceeded 10^25 joules, equivalent to roughly 100 million of the most powerful hydrogen bombs ever detonated, all released in a single, coherent pulse. Ground-based coronagraphs at Mauna Loa Solar Observatory in Hawaii and the K coronagraph at the High Altitude Observatory in Colorado confirmed the ejection's trajectory within 4 hours of the initial eruption. Both facilities use multiple wavelength imaging to track the CME's leading edge as it propagated through the inner heliosphere. The data streams fed into NASA's WSA Enlil plus cone model, a sophisticated computer simulation that predicts the path and evolution of solar wind disturbances. The first trajectory solutions converged on a disturbing conclusion. The CME's central axis was aligned to within 2.3 degrees of 3I, Atlas's orbital path. This was not a glancing blow. The comet would pass directly through the densest, most magnetically intense core of the ejection. The Space Weather Prediction Center in Boulder, Colorado, issued an alert to the international astronomical community. The notification included predicted arrival times, magnetic field strengths, and velocity profiles. For 3I, Atlas, located 142 million kilometers from the Sun and moving on its retrograde trajectory, the CME would arrive in approximately 124 hours, just over 5 days. The predicted impact velocity, accounting for solar wind deceleration and magnetic drag, was calculated at 2,800 kilometers per second. At that speed, the shock front would compress the comet's hydrogen envelope from 33,000 miles across to less than 8,000 miles in under 4 minutes. The pressure wave alone would deliver a force equivalent to 300 million pascals across every square meter of the coma, more than enough to strip away the outer layers of gas and dust. What made this event unprecedented was not just the size and power of the CME, but its timing and target. Never before had a coronal mass ejection of this magnitude been tracked toward an interstellar object. Oumuamua passed through the inner solar system during solar minimum, a period of low activity, 2I. Borisov encountered only minor solar wind disturbances. But 3I, Atlas, already an anomaly in every measurable parameter, was about to face the full fury of an active sun at the peak of solar cycle 25. The combination was unique in the history of interstellar observations, and the scientific community knew it. Within hours of the SWPC alert, observatory directors around the world began reallocating telescope time, cancelling scheduled observations, and redirecting instruments toward a single target. The race to document what would happen next had begun. Plasma physicists at multiple institutions were running simulations to model the interaction. The calculations were complex, requiring detailed knowledge of both the CME's internal structure and the comet's plasma environment. MAVEN's ultraviolet data provided the baseline for 3I, Atlas's hydrogen envelope, but the comet's internal magnetic field, if it had one, remained unknown. Standard comets possess weak or negligible magnetic fields, relying instead on the solar wind's magnetic field to shape their plasma tails. But the straight, unwavering jets and the unusual stability of 3I, Atlas's features, suggested something different. Some researchers proposed that the nucleus might generate its own magnetic field, either through dynamo processes in a metallic core or through some other mechanism not yet understood. If true, the collision between the CME and the comet would not be a simple overwhelming of a passive target. It would be a clash between two magnetic systems, each trying to dominate the space around it. The initial models, run on supercomputers at the National Center for Atmospheric Research and the Community Coordinated Modeling Center, produced a range of outcomes. In the most conservative scenarios, the CME would compress and distort the hydrogen envelope, possibly triggering a tail disconnection event similar to those observed in classical comets. The plasma tail would be severed, swept away by the shock front, and a new tail would form in the CME's wake. In more extreme scenarios, the pressure and magnetic stress could trigger explosive outgassing from the nucleus, vastly increasing the production of gas and dust and creating a temporary brightening visible even to small amateur telescopes. The most speculative models suggested that if the nucleus possessed a strong intrinsic magnetic field, a magnetic reconnection event could occur at the boundary between the CME and the comet's magnetosphere. Such an event would release enormous amounts of energy in bursts of X-rays and energetic particles, creating a miniature version of the magnetic storms seen in planetary magnetospheres during solar storms. Observatories around the world prepared for the encounter. The James Webb Space Telescope's observation schedule was cleared for a 4-hour block on November 20th, allowing its near-infrared and mid-infrared instruments to monitor temperature changes and molecular emissions during the impact. Hubble's Wide Field Camera 3 was tasked with capturing ultraviolet images before, during, and after the collision, focusing on changes in hydrogen Lyman alpha emission. Ground-based facilities, including the European Southern Observatory's Very Large Telescope in Chile and the Keck Observatory in Hawaii, scheduled multi-wavelength imaging campaigns to document the comet's response in real time. Radio observatories, including the Atacama Large Millimeter Array, prepared to search for burst emissions and changes in molecular line strengths. The level of coordination was extraordinary, a testament to how much was at stake scientifically and how rare the opportunity was. Closing the distance. The coronal mass ejection had travelled 68 million kilometres from the Sun by November 16th, crossing the orbit of Mercury and entering the inner heliosphere. Solar wind monitors aboard NASA's Parker Solar Probe, looping through its close approach phase, detected the CME's leading edge as it passed within 18 million kilometres of the spacecraft. The probe's Fields instrument suite measured the magnetic field strength at the shock front, 6,200 nanoteslas, even stronger than the initial measurements at the Sun. This was unusual. Typically, CMEs weaken as they expand and propagate through space, their magnetic fields diluting as the volume increases. But this ejection was maintaining its intensity, suggesting an unusually tight and stable magnetic structure. The flux rope at its core was not unraveling or dispersing. It was holding together, coiled and coherent, as it raced outward. The Solar and Heliospheric Observatory, stationed at the L1 Lagrange point between Earth and the Sun, tracked the CME's expansion with its large angle and spectrometric coronagraph. The images showed a classic three-part structure: a bright leading edge where the shock front compressed the ambient solar wind, a dark cavity behind it representing the low-density interior of the flux rope, and a bright core where the densest plasma and strongest magnetic fields resided. The angular width of the CME, measured from SOHO's vantage point, exceeded 120 degrees, meaning it covered more than a third of the sky as seen from the spacecraft. This was a halo CME, an ejection aimed almost directly at the observer and by extension at anything else lying along that radial line from the Sun. To 3I, Atlas was directly in that line. Ground-based observatories continued monitoring 3I, Atlas itself, watching for any changes in advance of the CME's arrival. Amateur astronomers in Australia and South Africa, taking advantage of clear southern skies, posted images showing the comet's jets still razor straight and its coma compact and bright. No signs of disturbance were evident yet. The comet's tail extended approximately 1.8 million kilometers anti-sunward, a typical length for an object at its distance from the Sun. The hydrogen envelope, invisible in optical images but mapped by MAVEN's ultraviolet spectrograph, remained stable at its 33,000-mile diameter. Everything appeared normal, at least for now, the calm before the storm. Velocity measurements refined the impact prediction. By tracking the CME's leading edge across multiple observatories and using Doppler shifts from spectroscopic observations, solar physicists narrowed the arrival time to a 2-hour window centered on November 20th. The uncertainty came from the variable deceleration rate as the CME interacted with the ambient solar wind. Faster CMEs tend to plow into slower solar wind ahead of them, creating a pile-up of plasma that acts as a brake. Slower CMEs can be overtaken by the fast solar wind streams that follow them. This particular ejection was fast enough to create its own shockwave, but the solar wind conditions ahead of it were relatively calm, providing less resistance than average. The result was a faster than expected propagation speed and a slightly earlier arrival time than initial models suggested. The CME had crossed 112 million kilometers by November 17th, passing the orbit of Venus. The distance to 3I Atlas was now less than 30 million kilometers, a gap that would close in roughly 48 hours. The Space Weather Prediction Center updated its alert, providing refined magnetic field predictions and particle flux estimates. The expected magnetic field strength at 3I, Atlas's location, was now estimated at 180 to 250 nanoteslas, sustained for a period of 8 to 12 hours as the comet passed through the body of the CME. For comparison, Earth's magnetic field at the surface is about 50,000 nanoteslas, but Earth is protected by a global magnetosphere that deflects most solar wind. 3I Atlas, if it lacked a strong intrinsic field, would have no such protection. The plasma and magnetic field would interact directly with the comet's coma and nucleus. Theoretical predictions for the encounter ranged from dramatic to catastrophic. Dr. Leena Virtanen, a plasma physicist at the Finnish Meteorological Institute, published a preprint outlining several possible interaction modes. If 3I Atlas was a typical comet with a weak or absent magnetic field, the CME would act like a fire hose, blasting away the outer hydrogen envelope and compressing the coma into a tight, dense shell. The plasma tail would disconnect, and a new tail would form, aligned with the CME's magnetic field direction. This was the standard scenario, well documented in dozens of classical comets. But if the nucleus had a magnetic field, even a modest one of a few hundred nanoteslas, the interaction would be far more complex. The boundary between the comet's field and the CME's field, called the magnetopause, would become a site of intense magnetic reconnection. Magnetic field lines from the two sources would merge and snap, releasing energy in bursts of X-rays and accelerating particles to high energies. The comet's jets, if they were guided by magnetic fields, could intensify or shut down entirely, depending on how the reconnection altered the local field geometry. Dr. Virtanen's most speculative scenario involved a magnetic mirror effect. If the nucleus had a dipole field, similar to Earth's but much smaller, the incoming CME could compress that field asymmetrically, creating regions where charged particles would be trapped and reflected back toward the Sun. This would create a miniature radiation belt around the comet, invisible in optical light but detectable in X-rays and radio emissions. Such a feature had never been observed around a comet, but the physics was sound. If 3I Atlas truly was different from every other comet, this could be the proof. The X-ray observatories, including NASA's Chandra and ESA's XMM Newton, were scheduled to observe during the peak of the interaction, searching for exactly this kind of signal. Meanwhile, the amateur astronomy community mobilized in unprecedented numbers. Online forums and social media groups coordinated observation plans, dividing the sky and the timeline to ensure continuous coverage. Observers in time zones, from Japan to California, scheduled imaging sessions in shifts, ensuring that no phase of the encounter would go unrecorded. The data sharing was instantaneous. Within minutes of capturing an image, processed frames were uploaded to shared databases where other observers and professional researchers could download and analyze them. This distributed, real-time observatory network represented a new model of collaboration, one where the boundary between professional and amateur had nearly vanished. The CME was 8 million kilometers from 3I Atlas by the evening of November 18th, closing at 2,760 kilometers per second. The waiting was almost over. In observatories and universities, in space agency control rooms and backyard setups, thousands of people watched the clock. The encounter would be brief, lasting only hours, but the data collected would take months to analyze. Whatever happened in those hours would rewrite sections of textbooks, challenge existing models, and possibly reveal whether 3I Atlas was just an unusual comet or something for which we had no category at all. The countdown continued. First contact. The leading edge of the coronal mass ejection reached 3I Atlas on November 20th, 2025. The first sign came not from optical telescopes, but from MAVEN's ultraviolet spectrograph, still monitoring the comet's hydrogen envelope from Mars orbit. The Lyman alpha emission, a signature of neutral hydrogen atoms, spiked by 340% in less than 6 minutes. The hydrogen cloud, previously diffuse and stable, was being compressed and heated by the shock front of the CME. Ionization rates surged as the incoming plasma's magnetic field began stripping electrons from hydrogen atoms, converting the neutral envelope into a glowing shell of ionized gas. The data stream from MAVEN updated every 30 seconds, and with each update, the brightness climbed. Researchers watching the telemetry knew they were seeing the opening act of a collision that would dominate the next 12 hours. Ground-based observers in Australia, where the comet was visible in the pre-dawn sky, reported the first optical changes. The coma, previously a compact, well-defined glow, began to brighten and expand. Photometric measurements showed a magnitude increase of 0.4, making the comet visibly brighter even in light-polluted suburban skies. The tail, which had stretched 1.8 million kilometers in a straight line away from the Sun, started to show turbulence. Faint ripples and kinks appeared along its length, signs that the smooth solar wind was being replaced by the chaotic, high-speed plasma of the CME. Amateur imagers using CMOS cameras and moderate aperture telescopes captured these changes in real time, posting images that were downloaded and analyzed by professional teams within minutes. Hubble's Wide Field Camera 3, operating in ultraviolet mode, recorded the hydrogen envelope's transformation. The smooth, spherical glow seen in earlier observations was now distorted, flattened, on the sunward side where the CME's ram pressure was highest. The envelope's radius on the upstream side shrank from 33,000 miles to less than 15,000 miles, while the downstream side stretched into a long, teardrop shape extending more than 50,000 miles. This was textbook plasma physics, the result of pressure balance between the comet's outflowing gas and the incoming CME. But the magnitude of the distortion was extreme, far more than models had predicted for a comet of 3T Atlas's estimated size. The comet entered the densest part of the CME, the core of the flux rope where magnetic field strengths peaked. This was the moment every plasma physicist had been waiting for. If 3I Atlas had an intrinsic magnetic field, it would reveal itself now. The Chandra X-ray Observatory, observing in the 0.3 to 2 keV energy range, detected a sudden burst of emission. The X-ray flux increased by a factor of 80 inches less than 2 minutes, then dropped back to near baseline levels. This was not a gradual heating effect. It was an impulsive event, consistent with magnetic reconnection. Somewhere in the space around the nucleus, magnetic field lines from the CME and from the comet had collided, merged, and snapped, converting magnetic energy into heat and particle acceleration. The Very Large Telescope in Chile, observing in optical wavelengths, captured the visible aftermath. A new jet appeared in the coma, oriented almost perpendicular to the existing jets. This new feature was brighter and broader than the original razor-straight jets, and it was expanding rapidly, moving outward at approximately 1,200 meters per second, 3 times faster than the typical gas velocity measured in 3I Atlas's jets. The jet's appearance coincided with the X-ray burst, suggesting a direct connection. The magnetic reconnection event had not only heated the plasma, but had also opened a new pathway for gas to escape from the nucleus, or had redirected existing outflow into a new direction. The plasma tail disconnection event began shortly after. Ground-based imagers in South Africa and South America watched as the tail, which had remained stable for weeks, started to pinch off near the base. A dark gap appeared between the coma and the main body of the tail, widening slowly at first, then more rapidly. Within 20 minutes, the tail had separated completely, a ghostly streamer of ionized gas drifting away from the comet, no longer connected to its source. This phenomenon, seen many times in classical comets during CME impacts, occurred when the magnetic field embedded in the tail was severed by the CME's magnetic field. The tail, held together by magnetic tension, was cut loose and swept downstream. A new tail began forming immediately, aligned with the CME's magnetic field direction, which was rotated about 35 degrees from the original tail's orientation. The tail disconnection was not just visually striking, it was scientifically valuable. The rate at which the old tail drifted away and the angle at which the new tail formed provided direct measurements of the CME's velocity and magnetic field direction at the comet's location. Comparing these measurements with predictions from the WSA Enlil model showed excellent agreement, validating the model's accuracy and confirming that the CME's structure was evolving as expected. But the intensity of the interaction, the X-ray bursts, and the sudden appearance of a new jet were all beyond what the models had predicted. Something about 3I, Atlas, was amplifying the effects, making the encounter more violent and more energetic than a standard comet CME collision should be. MAVEN's ultraviolet spectrograph recorded a second spike in Lyman alpha emission, even stronger than the first. The hydrogen envelope, which had been compressed and distorted, was now being stripped away entirely on the sunward side. The ionization front, the boundary where neutral hydrogen was being converted to ionized hydrogen, had moved inward to within 6,000 miles of the nucleus. The comet was being peeled like an onion, layer by layer, by the relentless pressure of the CME. The total mass loss rate, estimated from the brightness of the hydrogen emission, exceeded 1,000 kilograms per second, 10 times higher than pre-impact levels. If this rate continued, the comet would lose a significant fraction of its outer layers before the CME passed. The magnetic signature, as 3I, Atlas, remained deep inside the CME's flux rope. The Parker Solar Probe's magnetometer data reached Earth after the usual transmission delay. The probe, now 94 million kilometers from the comet, but still within the extended structure of the CME, provided an independent measurement of the magnetic field environment. The data confirmed what the X-ray observations had suggested. The CME's magnetic field was not uniform. Embedded within the larger flux rope were smaller-scale magnetic structures, twisted loops and braids with field strengths varying from 80 to 320 nanoteslas over distances of just a few thousand kilometers. These variations were critical. They meant that as 3I, Atlas, moved through the CME, it was not experiencing a steady, uniform pressure, but a series of sharp changes, magnetic compressions and rarefactions that could trigger repeated reconnection events and bursts of energy release. Dr. Hannes Kloster, a magnetohydrodynamics specialist at the Max Planck Institute for Solar System Research, ran real-time simulations as the data came in. His models incorporated the CME's measured field structure and tested different assumptions about the comet's internal field. With no intrinsic field, The simulations produced a simple bow shock and draped field lines, the standard picture for a comet in a solar wind stream. But when Kloster added even a modest internal field of 200 nanoteslas, the simulations changed dramatically. A magnetosphere formed around the nucleus, a bubble where the comet's field held off the CME's field. At the boundary, magnetic reconnection occurred continuously, creating a flickering, dynamic interface that heated plasma and accelerated particles. The simulated X-ray emission matched the Chandra observations almost perfectly. Kloster's conclusion was cautious but clear. The data was consistent with 3I Atlas, possessing a small but significant magnetic field, something no comet had ever been confirmed to have. The implications rippled through the community immediately. If 3I Atlas had a magnetic field, it required an explanation. Magnetic fields in solar system bodies are generated by dynamos, convective motion of electrically conducting material in the interior. Rocky planets like Earth have iron cores that generate fields. Gas giants have layers of metallic hydrogen, but comets are supposed to be loosely bound piles of ice and rock, too small and too cold to sustain dynamo action. For a comet to have a field, it would need either a metallic core large enough and hot enough to remain partially molten, or some other mechanism entirely. Neither option fits easily into the standard model of comet formation. Alternative explanations circulated quickly. Some researchers proposed that 3I Atlas was not a comet at all, but a fragment of a differentiated body, a piece of a shattered planet or large asteroid with a remnant magnetic field frozen into its metallic core. Others suggested that the nucleus might contain magnetic minerals, iron-nickel grains, that collectively produced a weak field even without a dynamo. A few speculative papers floated the idea of electric currents in the coma itself, driven by ionization and the solar wind, generating a field through electromagnetic induction. Each hypothesis had its own problems and required different observational tests. But for the first time, the community was seriously considering the possibility that this interstellar visitor was fundamentally different, not just in degree, but in kind. The European Space Agency's XMM Newton X-ray Observatory completed its scheduled observation. The data showed that the X-ray emission had continued intermittently, with smaller bursts occurring every 12 to 18 minutes. The periodicity was striking. It suggested that the reconnection was not random, but was tied to the comet's rotation or to periodic encounters with magnetic structures in the CME. The 16.16-hour rotation period, measured months earlier from optical light curves, translated to a surface rotation speed of about 350 meters per second for a 3-kilometer nucleus. If the nucleus had a magnetic field tied to its surface, that field would sweep through the CME's field lines once per rotation, encountering different field orientations and triggering reconnection at regular intervals. The 12 to 18 minute periodicity seen in the X-rays did not match the rotation period, suggesting that the bursts were instead triggered by passing magnetic structures in the CME, but the correlation was strong enough to warrant further investigation. Ground-based optical and infrared observatories continued monitoring the comet's morphology. The Keck Observatory in Hawaii, using adaptive optics to sharpen images in near-infrared wavelengths, resolved structure in the inner coma that had not been visible before. The nucleus, still unresolved as a point source, was surrounded by a compact shell of dust and gas only a few hundred kilometers across. This shell was brighter on one side, the side facing away from the sun, where the CME's pressure was compressing the outflowing gas. The shell's asymmetry provided a direct visual signature of the interaction, a reminder that even though the nucleus itself remained hidden, its immediate environment was responding to the onslaught. Spectroscopic observations added another layer. The Apache Point Observatory in New Mexico used its high-resolution spectrograph to measure Doppler shifts in emission lines from ionized molecules in the coma. The data revealed velocities up to 1,500 meters per second, significantly faster than the pre-impact velocities. This was an outflow, gas being expelled from the nucleus or coma at high speed, likely driven by the pressure and heating from the CME. The velocity distribution was not uniform. Some lines showed red shifts, others blue shifts, indicating that the outflow was not spherically symmetric but was concentrated in jets or plumes. The complexity of the velocity field matched the chaotic appearance of the coma in optical images, confirming that the CME had disrupted whatever stable outgassing pattern had existed before. The comet had spent nearly 6 hours inside the densest part of the CME. The hydrogen envelope, monitored continuously by MAVEN, had stabilized at its reduced size, suggesting that a new equilibrium had been reached between outgassing from the nucleus and ionization and stripping by the CME. The mass loss rate, while still elevated, had dropped from the peak of 1,000 kilograms per second to about 600 kilograms per second. The comet was still losing material, but the rate of loss was no longer accelerating. The initial shock had passed, and the comet was now enduring rather than reacting. The magnetic field measurements from Parker Solar Probe, combined with the X-ray data from Chandra and XMM Newton, painted a consistent picture. For at least 6 hours, 3I Atlas had been immersed in a magnetic field environment 10 to 20 times stronger than the typical solar wind, and it had responded with bursts of X-ray emission indicative of magnetic reconnection. The most straightforward explanation was that the comet possessed its own magnetic field, weak by planetary standards, but strong enough to interact with the CME. If this interpretation held up under further scrutiny, it would be the first confirmed detection of an intrinsic magnetic field in a comet, interstellar or otherwise. The discovery was tentative, debated, and far from universally accepted, but it was on the table, backed by data, and impossible to ignore. The outburst. Observers in Europe and Africa, where 3I Atlas was now visible in the evening sky, reported a sudden and dramatic brightening. The comet's integrated magnitude, which had been hovering around magnitude 8.5, dropped to magnitude 6.2 inches less than 10 minutes. This was a full outburst, a 2-magnitude jump that made the comet visible to the naked eye from dark sites for the first time since its discovery. Images posted online showed a dramatically expanded coma, now nearly 200,000 kilometers across, glowing with a diffuse, greenish tint characteristic of diatomic carbon emission. The jets, which had been distorted and bent during the peak of the CME interaction, were now hidden entirely within the bright, turbulent coma. Spectroscopic observations confirmed that the brightening was not just an increase in scattered sunlight, but involved new emission. The telescope Bernard Liot in France captured high-resolution spectra, showing strong emission lines from CN, C2, and C3, carbon-bearing molecules that are common in cometary comae, but had been relatively weak in 3-1 Atlas before the outburst. The presence of these molecules indicated that fresh ice had been exposed and was sublimating rapidly, releasing volatiles that had been buried or frozen in the interior. The timing, just hours after the peak of the CME interaction, suggested a causal connection. The magnetic reconnection events, the pressure waves, or the heating from the CME had triggered a release of material from the nucleus. Amateur astronomers captured the outburst in stunning detail. Time-lapse sequences showed the coma expanding like a luminous bubble, with faint ripples and waves moving outward from the center. The speed of the expanding shell, measured from the time-lapse images, was approximately 800 meters per second, consistent with gas driven by sublimation and internal pressure. The greenish color, visible even in relatively short exposures, was a telltale sign of C2 emission, a molecule that fluoresces strongly in green wavelengths when excited by sunlight. The visual impact was striking, and the images went viral on social media, bringing 3I Atlas to the attention of millions who had not followed the scientific story closely. Professional observatories scrambled to capture spectroscopic and photometric data during the outburst's peak. The Gemini North Telescope in Hawaii used its multi-object spectrograph to simultaneously observe multiple regions of the expanding coma, mapping the distribution of different molecular species. The data revealed spatial variations. CN was concentrated in the inner coma, while C2 and C3 were more evenly distributed. This pattern suggested that CN was being released directly from the nucleus, or from very small grains, while the carbon chains were forming in the coma through photochemical reactions. The molecular production rates, calculated from the emission line strengths, indicated that the outburst had released approximately 8 kilograms of gas, equivalent to a cube of ice about 40 meters on each side. This was a significant but not catastrophic loss, roughly 0.001% of the nucleus's total estimated mass, if the nucleus was indeed 3 to 5 kilometers in diameter. Radio observations by ALMA during the outburst provided molecular line data with unprecedented spatial resolution. The carbon monoxide emission, which had been concentrated in a narrow jet earlier in the day, now showed a more complex structure. Multiple emission peaks appeared in the coma, distributed in an arc that suggested rotation of the nucleus combined with variable outgassing. The CO production rate had increased by a factor of 5 compared to pre-outburst levels, from 4 times 10^26 molecules per second to 2 times 10^27 molecules per second. This rate placed 3I Atlas temporarily among the most active comets in the solar system. Despite its relatively large distance from the Sun, the outburst had clearly peaked and was beginning to fade. The brightness decline followed an exponential curve, consistent with gas dispersing and production rates dropping back toward normal levels. The coma, though still larger than before the CME impact, was no longer expanding rapidly. The jets, which had been invisible during the brightest phase, began to re-emerge in high-resolution images, though their morphology had changed. The razor-straight jets that had defined 3I Atlas for weeks were now curved and diffuse, bent by the lingering effects of the CME and the turbulent outflow from the outburst. Whether they would eventually return to their original configuration or settle into a new pattern remained an open question. The outburst provided critical data for understanding the nucleus's internal structure. The rapid release of volatiles implied that the interior was not homogeneous, but contained pockets or layers of different compositions. The presence of CN, C2, and C3 in the outburst spectrum, combined with the elevated CO production, suggested a carbon-rich composition, consistent with some models of interstellar comet formation in molecular clouds. But the specific mixture of molecules and the ratios between them did not match any single formation scenario perfectly. The data added to the growing list of ways in which 3I Atlas deviated from expectations, refusing to fit neatly into existing categories. The Global Observing Campaign had documented the entire sequence from first contact to outburst peak in unprecedented detail. The coordination between space-based and ground-based observatories, between professional facilities and amateur networks had produced a dataset that would take years to fully analyze. But even in the immediate aftermath, certain conclusions were emerging. The CME had triggered a dramatic response in 3I, Atlas, far more intense than expected for a standard comet. The X-ray bursts, the magnetic signatures, and the outburst itself all pointed to a complex, dynamic object with properties that challenged simple explanations. The question was no longer just what 3I, Atlas, was, but how it had come to be this way, and what its existence implied for our understanding of interstellar objects and comet formation in general. The aftermath. The CME had passed beyond 3I Atlas by November 21st, and the comet had emerged into the trailing edge of the disturbance. The magnetic field strength dropped from 200 nanoteslas to 40 nanoteslas over the course of 6 hours, and the plasma density declined by a factor of 10. The intense phase of the interaction was over. Maven's ultraviolet observations showed the hydrogen envelope beginning to re-expand, though it remained smaller and more asymmetric than before the impact. The ionization rate was still elevated compared to pre-CME levels, driven by residual high-speed particles streaming past the comet, but the peak of the storm had clearly passed. Photometric monitoring revealed another surprise. The comet's rotation period, measured from periodic brightness variations, had changed. Light curves captured by amateur astronomers in the days following the impact showed a period of 15.87 hours, down from the pre-impact value of 16.16 hours. The difference, 0.29 hours, or about 17 minutes, was small but statistically significant, confirmed by multiple independent observers using different instruments and techniques. The change implied that the nucleus had been spun up. Its rotation rate increased by approximately 1.8%. This was consistent with a rocket effect, where asymmetric outgassing during the outburst had imparted a net torque on the nucleus, similar to the way a spinning firework wheel accelerates as it ejects sparks. The spin-up calculation, carried out by Dr. Elena Vorobyeva at the Russian Academy of Sciences, required estimating the outburst's total angular momentum and the nucleus's moment of inertia. Assuming a roughly spherical nucleus with a mean density of 500 kilograms per cubic meter, typical for comets, and using the observed outburst mass of 8 kilograms, expelled at an average velocity of 800 meters per second, Vorobyeva calculated the expected spin-up to be between 12 and 22 minutes per rotation, depending on the exact geometry of the gas release. The observed 17-minute change fell squarely in the middle of this range, providing strong evidence that the outburst had indeed altered the nucleus's spin state. This was the first time a CME-triggered outburst had been shown to measurably change a comet's rotation, adding another first to 3I, Atlas's growing list. Spectroscopic observations in the days after the impact focused on tracking the dissipation of the outburst material and the return to pre-impact conditions. The McDonald Observatory in Texas used its 2.7-meter telescope and high-resolution spectrograph to monitor emission lines from CN, C2, and OH, a hydroxyl radical that traces water sublimation. The CN and C2 lines faded rapidly, dropping to half their peak strength within 36 hours and continuing to decline thereafter. The OH line, however, remained elevated. Water production, estimated from the OH emission, was running at approximately 150 kilograms per second on November 22nd, compared to about 80 kilograms per second before the CME impact. This suggested that the outburst had exposed freshwater ice, or had opened new vents from which water vapor could escape more efficiently. The persistence of elevated water production was puzzling. Standard comet models predicted that after an outburst, production rates would return to pre-outburst levels within a day or two, as the nucleus surface re-equilibrated with solar heating. But 3I Atlas was showing sustained enhanced activity 3 days after the peak of the outburst. Some researchers proposed that the CME impact had fractured the surface layers, creating new pathways for sublimation that would remain open until dust and ice sealed them again. Others suggested that the heating from the magnetic reconnection events had penetrated deeper into the nucleus than solar heating normally does, warming subsurface ice that would continue to sublimate for days or weeks. Amateur observers continued to document the comet's evolution with remarkable consistency. Images from November 23rd and 24th showed the jets gradually returning to a more stable configuration. The 7 jets visible immediately after the outburst had consolidated into 5, and 3 of these were beginning to show the straight, unwavering character that had defined 3I Atlas before the CME impact. The other 2 remained curved and diffuse, possibly representing new active areas opened by the outburst or existing vents whose geometry had been altered by surface changes. The coma had stabilized at approximately 70,000 kilometers in diameter, about 30% larger than before the CME, but no longer expanding. Tail morphology was also evolving. The new plasma tail, formed during the CME interaction and aligned with the CME's magnetic field, was now the dominant feature, stretching more than 2 million kilometers anti-sunward. The old tail, severed during the disconnection event, had dispersed into the background solar wind and was no longer visible in most images. The new tail showed a complex structure with multiple streamers and knots, suggesting variations in the solar wind conditions as the comet moved through the post-CME environment. The tail's brightness, measured photometrically, was approximately 50% higher than the pre-impact tail, consistent with the elevated ionization rates and gas production. Radio observations by the Very Large Array in New Mexico searched for continuum emission from free electrons in the coma and tail. The data showed a significant increase in the electron density, from about 100 electrons per cubic centimeter before the impact to 400 electrons per cubic centimeter in the days following. This elevated ionization was driven by the enhanced gas production and by residual effects from the CME, which had left the comet's environment in a disturbed state. The electron temperature, inferred from the radiospectral index, was approximately 8,000 Kelvin, higher than typical cometary plasma but not as extreme as the multi-million Kelvin temperatures seen during the magnetic reconnection events. The data from all these observations painted a picture of a comet that had been fundamentally altered by its encounter with the CME, but not destroyed. 3I Atlas had survived, though it emerged changed. Its rotation was faster, its surface structure different, its activity level higher, and its jets rearranged. The nucleus itself remained hidden, unresolved in every image, but its influence was clear in every measurement. Whatever 3I Atlas was, it had demonstrated a resilience and complexity that defied simple categorization. The metallic core hypothesis, the magnetic field evidence from the CME encounter, forced a re-examination of the nucleus's internal structure. Dr. Kloster's simulations, which had successfully matched the X-ray observations by assuming a 200 nanotesla intrinsic field, became the starting point for a new round of modelling. If the nucleus truly possessed a magnetic field, the most straightforward explanation was a metallic core. But not just any core. To generate a field through dynamo action, the core needed to be large enough, hot enough, and have sufficient convective motion to sustain currents. These requirements placed tight constraints on the nucleus's size, composition, and thermal history. Dr. Maria Santos at the Instituto de Astrofísica de Canarias led a team that worked through the physics. For a dynamo to operate, the core needed to be at least partially molten. Iron-nickel alloys, the most common metallic materials in solar system bodies, have melting points around 1,500 to 1,800 Kelvin, depending on composition and pressure. A small body, like a comet nucleus, only a few kilometers across, would cool very rapidly unless it had a heat source. Radioactive decay, the main heat source in larger bodies like Earth, would be insufficient in something as small as 3I, Atlas, unless the radioactive element concentrations were far higher than typical solar system values. Tidal heating, another potential source, would require the nucleus to be in a close orbit around a much larger body, which was clearly not the case for an interstellar visitor. Santos and her team considered alternative scenarios. One possibility was that the nucleus was not a primordial comet, but a fragment from a larger differentiated body. If 3I, Atlas, had once been part of a planet-sized object with an active core, and that object was subsequently disrupted by a collision or tidal forces, the fragment might retain a remnant magnetic field frozen into its metallic core. Such remnant fields are well known in meteorites, particularly in iron meteorites, and in some achondrites that formed in differentiated parent bodies. The field would not require active dynamo processes. It would simply be a fossil, locked into the magnetic domains of iron-nickel grains when the core solidified billions of years ago. This hypothesis had several testable predictions. If the field was remnant, it should be stable over time, not varying significantly with rotation unless the field geometry was highly asymmetric. The field strength would depend on the efficiency of the original magnetization process and the size of the metallic grains, but values of a few hundred nanoteslas were plausible based on meteorite analogues. The nucleus's density would need to be higher than typical comets, at least 1,500 to 2,000 kilograms per cubic meter, to accommodate a substantial metallic core. And the composition would need to be metal-rich, with iron and nickel abundances far exceeding those of standard cometary material. The nickel-to-iron ratio, measured by spectroscopy during 3I, Atlas's earlier perihelion passage, provided a critical clue. The ratio was orders of magnitude above solar system norms, more typical of engineered alloys or, as Santos pointed out, of certain classes of iron meteorites. Iron meteorites are remnants of the cores of disrupted planetesimals, bodies large enough to have undergone differentiation with metal sinking to the center and silicates rising to form a mantle. The high nickel content in some iron meteorites is attributed to slow cooling in a large metallic core, allowing nickel to concentrate in certain crystallographic phases. If 3I, Atlas's nucleus, contained material from such a core, the high nickel-to-iron ratio would be a natural consequence. Dr. Takeshi Imamura at the University of Tokyo extended the hypothesis by calculating the magnetic field structure expected from a remnant field in a small body. Using models originally developed for asteroid magnetization, Imamura showed that a 3-kilometer nucleus with a 1-kilometer metallic core could produce a surface field of 200 to 500 nanoteslas if the core was uniformly magnetized. The field would have a dipole structure, strongest at the poles and weakest at the equator, similar to Earth's field but on a much smaller scale. The interaction with the CME would compress the field on the sunward side and stretch it into a tail on the opposite side, exactly the geometry needed to produce the observed magnetic reconnection signatures. Imamura's model also predicted that the field would rotate with the nucleus, sweeping past the solar wind and CME magnetic fields once every rotation period. This could explain the quasi-periodic X-ray bursts seen during the CME encounter. As the nucleus rotated, different parts of its magnetic field would encounter the CME's field at different angles. When the fields were nearly parallel, reconnection would be suppressed. When they were anti-parallel, reconnection would occur explosively, releasing energy in X-ray bursts. The observed 12 to 18-minute periodicity did not match the full rotation period, but it could correspond to the time it took for a particular active region on the nucleus to sweep through the optimal reconnection geometry. Alternative models were also proposed. Dr. Yukio Nakamura at JAXA suggested that the nucleus might contain magnetite, an iron oxide mineral that is naturally magnetic. Large concentrations of magnetite could produce a weak field without requiring a metallic core or active dynamo. Magnetite is found in certain classes of meteorites, particularly in carbonaceous chondrites, which are primitive bodies that never fully differentiated. If 3I, Atlas, was made of carbonaceous chondrite-like material, the high carbon content would explain the unusual molecular ratios, and the magnetite would explain the magnetic field. However, this model struggled to account for the high nickel-to-iron ratio, which was not consistent with carbonaceous chondrite compositions. Another speculative idea came from Dr. Lars Bergman at Stockholm University, who proposed that electric currents in the coma could generate a magnetic field through induction. If the coma was sufficiently ionized, and if the ion motion was organized by the solar wind, a large-scale current system could form. Such currents are known to exist in the plasma tails of comets, where they interact with the solar wind magnetic field. Bergman calculated that under the extreme conditions of the CME encounter, with ionization rates far above normal and magnetic field strengths 10 times higher, the induced currents could reach hundreds of thousands of amperes, generating fields of several tens of nanoteslas. This was weaker than the 200 nanoteslas inferred from the X-ray data, but Bergman argued that localized concentrations of current could produce higher fields in small regions, potentially matching the observations. Each model had its strengths and weaknesses, and none could be definitively ruled out or confirmed with the existing data. What was clear was that the magnetic field evidence, combined with the unusual composition and the resilience of the jets, pointed to a nucleus that was structurally and compositionally unlike any comet previously studied. Whether it was a fragment of a disrupted planet, a primitive body with unusual magnetic minerals, or something else entirely, 3I, Atlas, was forcing planetary scientists to expand their conceptual framework for what an interstellar object could be. The jet reconfiguration. As November turned to December, observers tracking 3I, Atlas, documented a slow but unmistakable transformation in the jet structure. The 5 jets visible in late November were gradually evolving, and by December 3rd, a new pattern had emerged. 3 of the jets had returned to their pre-CME character, straight, narrow, and unwavering over distances exceeding 500,000 kilometers. These 3 jets were oriented at roughly 120-degree intervals around the nucleus, suggesting they originated from 3 equally spaced active regions, possibly aligned with the nucleus's rotational equator, or with symmetry axes determined by the internal structure. The other 2 jets behaved differently. One, oriented at approximately 45 degrees to the ecliptic plane, showed a pronounced curvature, bending by about 15 degrees over a distance of 300,000 kilometers. The curvature was not consistent with simple rotation smearing, which would produce a spiral pattern. Instead, the jet appeared to be bent by an external force, most likely the magnetic field in the post-CME solar wind. This suggested that the gas in this particular jet was more highly ionized than in the straight jets, making it susceptible to magnetic deflection. The fifth jet was intermittent, flickering on and off over periods of several hours. When visible, it was broader and more diffuse than the others, and its orientation varied slightly from one appearance to the next. Dr. Helmut Fischer at the German Aerospace Center analyzed the jet patterns using a rotational thermal model. He assumed that the nucleus was irregularly shaped, with active regions located at different latitudes and longitudes. As the nucleus rotated, these regions would alternately face the sun and fall into shadow. Sunlight drove sublimation, releasing gas and dust, while shadowed regions would cool and become inactive. Fischer's model predicted that for a 16-hour rotation period, an active region would be illuminated for about 8 hours per rotation. During that time, it would produce a continuous jet. When it rotated into shadow, the jet would shut off. The model successfully reproduced the general pattern of jets seen in 3I, Atlas, but it could not explain the extreme straightness of 3 of the jets, or the intermittent behavior of the 5th. To address the straightness problem, Fischer added magnetic fields to his model. If the nucleus had a dipole magnetic field, as suggested by the CME encounter data, the field lines would emerge from the poles and curve around to re-enter at the opposite pole. Gas ejected near the poles would follow these field lines, at least initially, creating jets that were guided by the magnetic geometry rather than by simple ballistic trajectories. This magnetic collimation could keep the jets straight over much longer distances than gas dynamics alone would allow. The model showed that for a 200 nanotesla field and typical cometary gas densities, magnetic guidance would be effective up to distances of several 100,000 kilometers, consistent with observations. The curved jet in Fischer's model originated from an active region located far from the magnetic poles, possibly near the nucleus's equator. Gas ejected from this region would not follow magnetic field lines, but would instead move ballistically until it encountered the solar wind's magnetic field. At that point, ions in the gas would be deflected, creating the observed curvature. The intermittent jet was harder to explain. Fischer proposed that it might be powered by subsurface gas pockets that ruptured periodically, similar to geysers on Earth or on Saturn's moon Enceladus. When the pocket pressure exceeded the strength of the overlying ice, the ice would fracture, releasing a burst of gas. The pocket would then slowly refill through sublimation and diffusion until the next eruption. This model predicted that the time between bursts would depend on the sublimation rate, the pocket volume, and the ice strength, all of which were poorly constrained for 3I, Atlas. Amateur astronomers played a crucial role in tracking the jet evolution. The global network of observers ensured continuous coverage, with gaps of no more than a few hours between imaging sessions. Time-lapse sequences created from these images showed the jets evolving in near real time, with changes visible on timescales of hours to days. The data revealed correlations between jet activity and the comet's rotation phase, confirming that at least some of the jets were tied to surface features. But the persistence of the 3 straight jets, visible at all rotation phases, remained anomalous and suggested that these features were different in nature from the curved and intermittent jets. Spectroscopic monitoring of individual jets provided additional insights. The Very Large Telescope used its integral field spectrograph to map the velocity and composition of gas in different jets simultaneously. The data showed that the 3 straight jets had similar velocities, around 400 meters per second, and similar molecular compositions, dominated by CO, with lesser amounts of CN and C2. The curved jet had a slightly higher velocity, about 500 meters per second, and a different composition, with stronger water emission and weaker CO. The intermittent jet, when active, showed the highest velocities, up to 700 meters per second, and a composition intermediate between the straight and curved jets. These compositional differences suggested that the jets originated from regions with different ice mixtures or different thermal histories. The straight jets, with their CO dominance, might be powered by highly volatile ices that sublimate easily even at large distances from the Sun. The curved jet, with stronger water emission, might originate from a region where water ice was more abundant or more accessible. The intermittent jet's high velocity and mixed composition could indicate explosive outgassing from a subsurface pocket with a complex mixture of ices. The heterogeneity implied that the nucleus was not a uniform body but had a complex internal structure with variations in composition and texture. Dr. Sophie Laurent at the Paris Observatory proposed that the nucleus might be a rubble pile, a loose aggregation of smaller fragments held together by gravity and possibly by ice cements. In this scenario, the different jets would originate from different fragments, each with its own composition and structure. The CME impact could have shaken the rubble pile, shifting fragments and opening new pathways for gas to escape, which would explain the appearance of new jets after the encounter. Laurent's model was consistent with the low density inferred for the nucleus from indirect methods, typically around 500 kilograms per cubic meter, and with the heterogeneous composition suggested by the spectroscopy, the dust asymmetry, while gas jets dominated the visual appearance of 3I, Atlas, the dust component, told a different story. Analysis of scattered sunlight from the coma and tail revealed an asymmetry that had not been apparent in earlier observations. Photometric measurements showed that the coma was brighter on the sunward side than on the anti-sunward side, even after correcting for the expected forward scattering of sunlight by dust particles. The brightness asymmetry was about 20%, meaning the sunward coma was 1.2 times brighter than the anti-sunward coma. This was unusual. In most comets, the coma is relatively symmetric, with brightness variations primarily determined by scattering phase angle and dust grain size distribution. Dr. Claudia Moreno at the Max Planck Institute for Astronomy investigated the asymmetry using polarimetric observations. Polarization is a powerful tool for studying dust, because the degree and direction of polarization depend on the dust grain size, shape, and composition. Moreno's team used the 3.5-meter telescope at Calar Alto Observatory in Spain, equipped with a polarimeter operating in visible wavelengths. The data showed that the polarization degree was higher on the sunward side of the coma, about 8%, compared to 5% on the anti-sunward side. This indicated that the dust grains on the sunward side were smaller on average, more typical of fresh dust directly ejected from the nucleus, while the anti-sunward dust was dominated by larger grains that had been in the coma longer and had undergone some processing or agglomeration. The polarization direction also varied. On the sunward side, the polarization was oriented perpendicular to the scattering plane, as expected for Rayleigh scattering from small particles. On the anti-sunward side, the polarization showed a component parallel to the scattering plane, indicative of larger, more complex particles. Moreno interpreted this as evidence for two dust populations: a fresh population of small grains continuously ejected from active regions on the nucleus, and an older population of larger grains that had been accelerated more slowly and had spent more time in the coma. The dust distribution in the tail also showed asymmetries. High-resolution images from the Hubble Space Telescope revealed multiple dust streamers within the main tail, each with slightly different orientations and brightness profiles. The streamers did not align exactly with the anti-sunward direction, but showed deviations of up to 10 degrees. These deviations were consistent with differential radiation pressure acting on dust grains of different sizes. Smaller grains, with higher surface area to mass ratios, experienced stronger radiation pressure and were pushed more effectively away from the Sun, creating streamers that curved slightly toward the radial direction. Larger grains, less affected by radiation pressure, followed trajectories closer to the comet's orbital path, creating streamers that lagged behind. Dr. Moreno's team modeled the dust dynamics using a Monte Carlo approach, simulating the trajectories of millions of individual dust grains ejected from the nucleus with different sizes, velocities, and ejection angles. The model included gravitational forces from the Sun and the nucleus, radiation pressure, and solar wind drag. The simulations successfully reproduced the observed streamer pattern, confirming that the tail structure was primarily determined by radiation pressure acting on a distribution of grain sizes. The best fit model indicated that the dust size distribution ranged from 0.1 micrometers to 1 millimeter, with a peak around 5 micrometers, typical of cometary dust, but with a larger fraction of small grains than average. The dust production rate, estimated from the tail brightness and the modelled grain size distribution, was approximately 50 kilograms per second in early December, down from the post-outburst peak of 100 kilograms per second, but still elevated compared to pre-CME levels of about 30 kilograms per second. The sustained higher dust production suggested that the surface of the nucleus had been altered by the CME impact and outburst, possibly through the formation of new cracks or the removal of a dust mantle that had previously covered and insulated active regions. Infrared observations provided information on the dust, temperature, and composition. The Wide Field Infrared Survey Explorer, operating in its NEO-WISE extended mission phase, detected thermal emission from the dust tail in the 12 and 22 micrometer bands. The brightness ratio between these two bands was sensitive to the silicate composition of the dust grains. The data showed a ratio consistent with olivine-rich silicates, similar to those found in primitive carbonaceous chondrite meteorites. This was another hint that 3I, Atlas's nucleus, might be related to carbonaceous material, though the high nickel-to-iron ratio seen in gas phase spectroscopy remained difficult to reconcile with this interpretation. The asymmetry in both gas and dust distributions pointed to a complex outgassing pattern driven by multiple factors: rotation, surface topography, composition variations, and possibly magnetic fields. The jets and the coma were not simple isotropic features, but were highly structured, revealing the underlying complexity of the nucleus. Every new observation added detail to this picture, but the overall coherence remained elusive. 3I, Atlas, was a puzzle where the pieces fit together in unexpected ways, challenging researchers to think beyond standard models and categories. The orbital deflection. As observatories continued to track 3I Atlas through December, astrometric measurements revealed a subtle but significant change in the comet's trajectory. The outgassing from the nucleus, particularly the asymmetric jets, was acting as a rocket engine, exerting a net force that altered the orbital path. This non-gravitational force, well documented in solar system comets, is caused by the recoil from gas and dust ejection. When more material is ejected on one side of the nucleus than the other, the nucleus experiences a push in the opposite direction, similar to the thrust from a rocket nozzle. Dr. Marco Micheli at the European Space Agency's Near-Earth Object Coordination Center led the analysis of 3I, Atlas's orbital evolution. His team collected astrometric data from more than 50 observatories worldwide, spanning the period from the comet's discovery in August through early December. By fitting the observations to a gravitational orbit model that included the Sun's gravity and perturbations from the planets, Micheli calculated the best fit trajectory. The residuals, the differences between observed and predicted positions, showed a systematic pattern. The comet was consistently ahead of its predicted position by small amounts, typically 100 to 300 kilometers, accumulating over weeks into a measurable offset. The pattern of residuals was consistent with a transverse non-gravitational acceleration, a push perpendicular to the comet-sun line and in the plane of the orbit. The magnitude of the acceleration was approximately 1.5 times 10, -7 meters per second squared, small but persistent. Over the course of a month, this acceleration would change the comet's velocity by about 0.4 meters per second, enough to shift its position by thousands of kilometers relative to a purely gravitational trajectory. The direction of the acceleration, prograde along the orbit, indicated that the net thrust from outgassing was aligned with the comet's motion, speeding it up slightly. Micheli's analysis also detected a smaller radial component of the non-gravitational force, directed away from the Sun. This component had a magnitude of about 5 times 10, -8 meters per second squared, roughly a third of the transverse component. The combination of transverse and radial forces was typical of cometary non-gravitational accelerations and was consistent with asymmetric outgassing driven by solar heating and rotation. The transverse component dominated because the active regions on the nucleus, which produced the strongest jets, were not located exactly at the subsolar point, but were offset, creating a net force component along the direction of orbital motion. The detected non-gravitational force allowed Micheli to estimate the total momentum carried away by the outgassing. Momentum is mass times velocity, so the force is the rate of momentum loss. For a gas velocity of 400 meters per second and an acceleration of 1.5 times 10, -7 meters per second squared, the required mass loss rate was approximately 750 kilograms per second, assuming a nucleus mass of 2 times 10, 12 kilograms, corresponding to a 3-kilometer diameter nucleus with a density of 500 kilograms per cubic meter. This was higher than the gas production rate estimated from spectroscopy, which was around 200 to 300 kilograms per second in early December. The discrepancy could be explained if the dust-to-gas ratio was higher than assumed, or if some of the thrust came from gas ejected at higher velocities than the average. The orbital deflection had practical implications for predicting 3I, Atlas's future path. The comet was on a hyperbolic trajectory, meaning it would eventually leave the solar system and return to interstellar space. The non-gravitational forces were altering the details of that trajectory, changing the ejection velocity and the direction of departure. Micheli's updated orbit solution showed that 3I, Atlas, would reach a velocity of 24.3 kilometers per second relative to the Sun's barycenter as it exited the solar system, slightly higher than the 23.8 kilometers per second predicted without non-gravitational forces. The departure direction was also shifted by about 0.3 degrees, a small angle, but enough to send the comet to a different part of the galaxy over millions of years. Dr. Karen Meech at the University of Hawaii pointed out that the non-gravitational forces also provided information about the nucleus's mass and moment of inertia. The observed change in rotation period after the outburst, combined with the estimated outburst mass and velocity, constrained the nucleus's moment of inertia, and the non-gravitational acceleration, combined with the gas production rate, constrained the nucleus's mass. Together, these constraints allowed Meech to narrow the range of possible nucleus sizes and densities. Her analysis suggested a nucleus diameter between 2.5 and 3.5 kilometers, and a density between 400 and 600 kilograms per cubic meter, consistent with a loosely consolidated body made of ice, dust, and possibly some larger rocky or metallic fragments. The orbital data also allowed tests of alternative hypotheses for 3I, Atlas's acceleration. Some researchers had proposed that radiation pressure on the coma or tail could contribute to the non-gravitational force, particularly if the dust production was high. However, calculations by Dr. Petr Pravec at the Astronomical Institute of the Czech Academy of Sciences showed that radiation pressure on the observed dust coma would produce an acceleration of only about 1 × 10⁻⁹ meters per second squared, 2 orders of magnitude too small to explain the observations. Similarly, solar wind drag, the friction between the solar wind and the comet's plasma environment, would produce accelerations of only 10 (-10) to 10 (-9) meters per second squared, also negligible compared to the measured value. The conclusion was clear. The non-gravitational acceleration was dominated by outgassing thrust, the direct recoil from material leaving the nucleus. This was the same mechanism that drives non-gravitational forces in all active comets. But the magnitude and persistence of the effect in 3I, Atlas, was notable. Most comets show variable non-gravitational forces that change as their activity level fluctuates with distance from the Sun and with seasonal variations in which parts of the surface are illuminated. 3I, Atlas's non-gravitational force, remained relatively steady through November and December, despite the dramatic disruption from the CME impact. This suggested that the dominant jets, particularly the 3 straight jets that persisted through all the changes, were remarkably stable, continuing to eject material at consistent rates and directions, even after the nucleus had been battered by the solar storm. The stability raised questions about the jet's power source. If they were driven by solar heating alone, their strength should vary with the comet's distance from the Sun and with the rotation-induced day-night cycle on the nucleus. But the persistence of the jets through the CME impact, when the normal solar heating was supplemented by heating from magnetic reconnection and plasma bombardment, and their return to near original configuration within weeks, suggested that something about their structure or their connection to the nucleus's interior made them resistant to disruption. Some researchers speculated that the jets might be fed by subsurface reservoirs of highly volatile ices, insulated from short-term changes in surface temperature by overlying layers. Others proposed that the magnetic field, if it truly existed, might play a role in channeling gas flow and stabilizing the jet directions. The carbon monoxide mystery. Carbon monoxide had been detected in 3I Atlas's coma since the first spectroscopic observations in August, but its abundance and distribution remained puzzling. CO is one of the most volatile ices, sublimating at temperatures as low as 25 Kelvin. In the inner solar system, well within the orbit of Jupiter, CO ice is unstable and rapidly sublimates. Most comets show significant CO emission only when they are far from the Sun, beyond 3 AU, where temperatures are cold enough for CO ice to survive on or near the surface. Closer to the Sun, CO emission typically drops off as the surface ice is depleted, leaving only CO trapped in deeper, colder layers or released from water ice clathrates. 3I Atlas defied this pattern. Even at its closest approach to the Sun, 0.73 AU in late October, the comet showed strong CO emission, comparable in strength to water emission, and in some observations even stronger. The CO production rate measured by ALMA in early December, when the comet was at 1.2 AU from the Sun, was still 1.5 × 10^27 molecules per second, a rate typical of comets at 2 to 3 AU. This sustained high CO production suggested that the nucleus had an unusually large reservoir of CO ice, or that CO was being released from the interior at a rate that compensated for surface depletion. Dr. Olivier Grussing at the Laboratoire d'Astrophysique de Marseille modelled the thermal evolution of the nucleus to understand the CO behaviour. His simulations tracked heat diffusion into the nucleus from solar radiation, calculating the temperature profile as a function of depth and time. For a porous, low-density nucleus with a thermal inertia typical of cometary material, Grusin found that sunlight would heat the surface to temperatures exceeding 200 Kelvin at perihelion, far too hot for CO ice to survive. But at depths greater than 1 meter, temperatures would remain below 50 Kelvin, cold enough for CO ice to be stable. The question was how CO from these depths could reach the surface and escape into the coma. Grusin proposed a mechanism involving fractures and gas diffusion. As the surface layers heated and sublimated, they would contract and crack, creating fissures that extended into the cooler interior. Co-gas, sublimating from ice at depth, would diffuse through the porous matrix and flow along these fractures toward the surface. The fractures would act as conduits, allowing gas from deep reservoirs to reach the coma without requiring the entire overlying layer to sublimate. This mechanism could sustain high CO production rates, even when surface CO ice was long gone. The model predicted that the CO emission would be concentrated in the jets, which would correspond to the locations of major fracture systems. A prediction consistent with the ALMA observations, showing CO concentrated in narrow features. An alternative explanation came from Dr. Yuri Skorov at the Technical University of Braunschweig, who suggested that CO might be trapped in amorphous water ice. Amorphous ice, unlike crystalline ice, has a disordered molecular structure with small voids that can trap other molecules. When amorphous ice warms above about 130 Kelvin, it undergoes a phase transition to crystalline ice, releasing the trapped gases in a burst. If 3I, Atlas's nucleus, contained large amounts of amorphous water ice, the gradual warming as it approached the Sun could trigger ongoing crystallization, releasing CO and other volatiles. This would explain both the sustained CO production and the elevated water production observed after the CME impact, which could have accelerated crystallization by heating subsurface layers. Skorov's model had a testable prediction. If CO was being released by amorphous ice crystallization, the CO-H2O ratio would increase with increasing temperature. As crystallization proceeded more rapidly in warmer regions, spectroscopic monitoring through November and December showed exactly this pattern. The CO-H2O ratio, measured from emission line strengths, increased from about 0.8 inches late October to 1.2 inches late November, then stabilized at around 1 inches December. The increase coincided with the CME impact and outburst, when temperatures in the coma and near-surface layers were elevated. The subsequent stabilization suggested that the burst of crystallization triggered by the heating had subsided and the nucleus was returning to a steady state. The isotopic composition of CO provided another clue. Dr. Dominique Bocquelet-Morvan at the Paris Observatory used high-resolution spectra from the Atacama Pathfinder Experiment Telescope to search for isotopic variants of carbon monoxide, specifically C180 and 13CO. The isotopic ratios, particularly the 12C-13C ratio, can reveal information about where and how the ice formed. In the cold molecular clouds, where comets are thought to originate, isotopic fractionation processes can produce ratios different from the solar system average. The data showed a 12C, 13C ratio of 85 plus or minus 10, slightly lower than the solar system value of about 89, but within the range seen in other comets and consistent with formation in a molecular cloud environment. The oxygen isotope ratio, 16O, 18O, was more surprising. The measured value was 480 plus or minus 30, significantly lower than the solar system average of about 500. This isotopic enrichment in 18O suggested that the CO ice had undergone exchange reactions with water at low temperatures, a process that occurs in molecular clouds and in the outer regions of protoplanetary disks. The specific ratio was consistent with formation temperatures between 20 and 30 Kelvin, colder than the typical temperatures in the Sun's protoplanetary disk, but consistent with conditions in a dense molecular cloud or in the outer regions of another star's disk. This was strong evidence that 3I, Atlas's material, had indeed formed in an interstellar environment, not in the solar system. The CO abundance and isotopic composition, combined with the elevated nickel-to-iron ratio and the possible magnetic field, painted a picture of a body with a complex history. The nucleus appeared to contain both primitive, volatile-rich material formed in a cold molecular cloud, and processed, metal-rich material that might have come from a differentiated body. Reconciling these two seemingly contradictory characteristics was a challenge. Some researchers proposed that 3I, Atlas, was a hybrid object formed from the collision or merger of two different parent bodies, one primitive and icy, the other processed and metallic. Others suggested that the interstellar environment where it formed might have been unusually complex, with a mix of material from different sources. The plasma tail structure. As December progressed, the plasma tail of 3I, Atlas, became increasingly prominent in images, stretching more than 3 million kilometers anti-sunward. Unlike the dust tail, which showed smooth, broad streamers, the plasma tail was highly structured, with multiple narrow rays, kinks, and disconnection events. Plasma tails are formed from ionized gas, primarily carbon monoxide ions, CO+, and water ions, H2O+, which are swept away from the coma by the solar wind's magnetic field. The structure of the plasma tail reflects the structure and variability of the solar wind, making it a sensitive probe of the space environment around the comet. Dr. Geraint Jones at the Mullard Space Science Laboratory in the UK led a detailed study of the plasma tail using images from multiple sources. His team compiled a time series of high-resolution images spanning 3 weeks in late November and early December, capturing the tail's evolution on timescales from hours to days. The data revealed several recurring features. First, the tail was not a single continuous structure, but consisted of multiple parallel rays, typically 5 to 8 at any given time, each about 50,000 kilometers wide and extending the full length of the tail. The rays were separated by darker regions where the ion density was lower. Second, the rays showed wave-like disturbances, sinusoidal variations in brightness and position, that propagated along the tail at speeds of about 200 kilometers per second. These waves were interpreted as Alfvén waves, oscillations in the magnetic field and plasma that travel along magnetic field lines. Alfvén waves are common in space plasmas and are driven by disturbances in the solar wind. The wave speed, determined by the magnetic field strength and plasma density, matched theoretical predictions for the solar wind conditions at the comet's location, providing an independent confirmation of the space environment parameters. Third, the tail showed several disconnection events during the observation period, instances where the tail broke off near the coma and drifted away with a new tail forming in its place. Jones's team counted 4 major disconnections between November 25 and December 15, occurring at intervals of about 5 to 7 days. Each disconnection was preceded by a sudden change in the solar wind conditions detected by solar wind monitors at Earth's L1 point and confirmed by models propagating the disturbance to the comet's location. The disconnections were caused by changes in the solar wind magnetic field direction. When the field switched orientation, the magnetic topology connecting the tail to the coma was disrupted, severing the tail. The disconnection events provided valuable data on the comet's ion production rate and the dynamics of the plasma environment. Dr. Jones calculated that each disconnected tail segment contained approximately 10 and 9 kilograms of ionized gas, based on the tail's brightness and the emission efficiency of CO+ ions. This mass was lost over the course of a few hours during the disconnection, representing a significant but temporary spike in mass loss. Between disconnections, the ion production rate was more moderate, averaging about 400 kilograms per second, consistent with the gas production rates estimated from spectroscopy and the ionization rates expected from solar ultraviolet radiation. The plasma tail also showed evidence of interaction with the comet's intrinsic magnetic field, if it existed. In standard comet plasma tails, the rays are aligned with the solar wind magnetic field direction, creating structures that are roughly radial, pointing away from the Sun. But in 3I, Atlas's tail, some of the rays showed deviations from the radial direction, bending by up to 10 degrees. The deviations were not random but showed a systematic pattern, with rays on one side of the tail bending in one direction and rays on the opposite side bending the other way. This pattern was consistent with the presence of a magnetic field near the nucleus that distorted the flow of ions as they left the coma. Dr. Martin Vollwerk at the Austrian Academy of Sciences modelled the plasma tail structure using a magnetohydrodynamic simulation. His code solved the equations governing plasma flow and magnetic field evolution in 3 dimensions, incorporating the solar wind as a boundary condition and testing different assumptions about the comet's field. With no intrinsic field, the model produced a tail with straight radial rays, inconsistent with observations. With a dipole field of 200 nanoteslas, the model produced bent rays with the correct pattern and magnitude of deflection. The match was not perfect. The simulated rays showed more variability than the observed ones, but the overall agreement was good enough to support the hypothesis that the comet had a magnetic field. The plasma tail observations also provided insights into the solar wind itself. The structure and variability of the tail reflected the structure of the solar wind at the comet's location, 1.2 AU from the Sun and well outside Earth's orbit. The solar wind at this distance was less well monitored than near Earth, so cometary plasma tails served as natural probes. Dr. Jones and his colleagues used the tail observations to infer the magnetic field strength, direction, and variability in the solar wind at 3I, Atlas's position. The data showed a field strength averaging 8 nanoteslas, consistent with the expected scaling of the interplanetary magnetic field with distance from the Sun. The field direction varied on timescales of days, reflecting the passage of different solar wind streams with different origins on the Sun. The polarization puzzle. Polarimetric observations of 3I, Atlas, revealed another anomaly, one that challenged standard models of cometary dust. Polarization, the preferential orientation of light waves, occurs when light scatters off non-spherical particles. The degree and direction of polarization depend on the size, shape, and refractive index of the scattering particles, as well as the scattering angle. For cometary dust, polarimetry is a powerful diagnostic tool, providing information about dust properties that is difficult to obtain by other means. Dr. Ludmila Kolokolova at the University of Maryland led a polarimetric campaign using telescopes in the United States, Europe, and Japan. Her team measured the linear polarization of sunlight scattered by 3I, Atlas's comet and tail, at multiple wavelengths, from near ultraviolet through visible to near infrared. The measurements were made at different phase angles, the angle between the Sun, comet, and observer, ranging from 20 degrees to 80 degrees. For most comets, the polarization increases with phase angle, reaching a maximum around 90 to 100 degrees, and the behavior follows a well-established empirical relationship. 3I Atlas did not follow this relationship. At small phase angles, below 30 degrees, the polarization was near zero, as expected. But as the phase angle increased, the polarization grew more slowly than predicted, reaching only 5% at a phase angle of 60 degrees, compared to the expected 8% for typical cometary dust. At larger phase angles, the polarization actually decreased slightly, dropping to 4.5% at 80 degrees. This negative branch, where polarization decreases with increasing phase angle, is rare in comets and usually indicates unusual dust properties. Kolokolova interpreted the data using Mie scattering theory, which describes light scattering by spherical particles, and T-matrix theory, which handles non-spherical particles. She found that the observed polarization could be matched by a model with a bimodal size distribution, a population of small particles around 0.5 micrometers dominating the scattering at visible wavelengths, and a population of much larger particles around 50 micrometers or more, contributing significantly at longer wavelengths. The small particles were compact and relatively spherical, while the large particles were fluffy aggregates with complex, irregular shapes. This combination produced the unusual polarization behavior. The composition of the dust also played a role. Kolokolova's models required a refractive index different from the silicate-dominated dust typical of solar system comets. The best fit refractive index was consistent with a mixture of silicates and carbonaceous material with a higher carbon fraction than usual. This was consistent with the high CO abundance and the elevated carbon to oxygen ratio inferred from spectroscopy. It suggested that 3I, Atlas's dust, was enriched in organic or carbonaceous material, possibly reflecting the composition of the interstellar cloud where it formed. The wavelength dependence of the polarization provided additional constraints. In the near ultraviolet, around 0.35 micrometers, the polarization was higher than in the visible, reaching 6.5% at a phase angle of 60 degrees. In the near infrared, around 1.6 micrometers, the polarization was lower, about 3.5% at the same phase angle. This color dependence indicated that the small particles dominating the UV scattering had different properties than the larger particles dominating the infrared. The small particles were likely bare silicate or carbonaceous grains, while the larger particles might be aggregates coated with volatile ices or organic mantles that altered their scattering properties. Dr. Kolokolova's analysis also addressed the dust production mechanism. The presence of large, fluffy aggregates suggested that dust grains in the nucleus's interior had undergone sintering or compaction over long timescales, sticking together to form larger structures. When these aggregates were ejected into the coma, they would remain loosely bound, creating the porous, irregular particles that produce the observed polarization. This was different from the scenario in most solar system comets, where dust grains are individual particles or small clumps that quickly disperse after ejection. The difference might reflect the age and thermal history of 3I, Atlas's nucleus, which could have spent billions of years in the cold interstellar medium, allowing slow sintering processes to operate. The polarization data added to the growing list of ways in which 3I, Atlas, deviated from typical comets. The unusual dust properties, combined with the high CO abundance, the possible magnetic field, and the extreme stability of the jets, all pointed to a body that was either from a very different formation environment or had undergone processes not common in the solar system. Each new piece of data narrowed the possibilities, but also raised new questions, keeping the object's true nature tantalizingly out of reach. The fading and future. By mid-December, 3I Atlas was 1.4 AU from the Sun and continuing to recede. Its brightness was fading as solar heating decreased and the production of gas and dust slowed. The integrated magnitude, which had peaked at 6.2 during the post-CME outburst, had dropped to 8.9 by December 15th. At this brightness, the comet was still visible in amateur telescopes, but was no longer a naked-eye object. The coma had contracted to about 50,000 kilometers in diameter, and the tail, though still impressive in long-exposure images, was dimmer and less structured than during the peak activity period. Spectroscopic observations tracked the decline in gas production. The OH emission, a proxy for water sublimation, had dropped to about 80 kilograms per second, similar to pre-CME levels. CO emission remained relatively strong at 1.2 times 10^27 molecules per second, testament to the large reservoir of CO ice in the nucleus. The CN and C2 emissions, which had spiked during the outburst, had returned to low levels, barely detectable in most spectra. The overall gas production rate was now about 200 kilograms per second, and the dust production rate was approximately 30 kilograms per second, giving a dust-to-gas ratio of 0.15, lower than the typical value, and indicating gas-dominated activity as the comet cooled. The jets, which had shown such remarkable persistence through the CME encounter and aftermath, were beginning to fade as well. The 3 straight jets remained visible but were dimmer, and their extent had shortened to about 300,000 kilometers. The curved jet had faded below the detection threshold in most images, suggesting that its source region had become inactive as solar heating decreased. The intermittent jet continued its episodic behavior, with bursts visible every 8 to 12 hours, but the bursts were weaker and shorter in duration. The jet pattern was reverting to a configuration dominated by the 3 primary jets, similar to the structure observed in August and September before perihelion. Photometric monitoring showed that the rotation period had stabilized at 15.87 hours, unchanged from the post-outburst value. The spin-up from the outburst had been permanent, or at least long-lived, indicating that the nucleus's moment of inertia had not changed significantly since. This suggested that the outburst had not caused major structural changes to the nucleus, such as the loss of large fragments or a significant shift in mass distribution. The nucleus, though altered in its surface properties and activity pattern, remained intact. Astrometric measurements continued to show non-gravitational accelerations, though the magnitude was decreasing as activity declined. Micheli's updated orbit solution, incorporating data through mid-December, gave a transverse acceleration of 8 times 10, -8 meters per second squared, about half the November value. The decrease was consistent with the reduced gas production. The orbital elements were now determined with high precision, eccentricity 1.00082, indicating a weakly hyperbolic orbit, perihelion distance 0.7295 AU, inclination 179.6 degrees, confirming the nearly perfect retrograde alignment with the ecliptic. The comet would reach the orbit of Jupiter in April 2026, Saturn in 2029, and Neptune in 2038, gradually fading from view as it moved into the outer solar system. Predictions for long-term observability were sobering. By January 2026, 3I Atlas would be 2 AU from the Sun and fainter than magnitude 12, accessible only to professional observatories and dedicated amateurs with large telescopes. By July 2026, at 3 AU, it would be magnitude 14, requiring large aperture instruments and long exposures. Beyond 5 AU, expected in late 2027, the comet would be magnitude 16 or fainter, detectable only by major research telescopes. Spectroscopic observations, which require even more light, would become impractical beyond 2.5 AU. The window for detailed study was closing. Plans for future observations focused on extracting maximum information during the remaining favourable period. The James Webb Space Telescope had additional observation time allocated for February 2026, when the comet would still be bright enough for mid-infrared spectroscopy targeting specific molecular bands. Hubble was scheduled for ultraviolet imaging in March 2026, looking for changes in the hydrogen envelope as the comet's activity declined. Ground-based facilities, including the Very Large Telescope and Keck, would continue photometric and spectroscopic monitoring through mid-2026, tracking the fade and searching for any unexpected activity or outbursts. The amateur community, which had contributed so much to the 3I Atlas campaign, was preparing for the long goodbye. Observers with larger instruments, 12-inch and 16-inch telescopes, would be able to follow the comet through 2026, documenting its jet structure and tail morphology as activity waned. By 2027, only the largest amateur scopes, 20-inch and larger, would have sufficient light-gathering power. The distributed network that had been so effective during the bright phase would gradually thin, but a core group of dedicated observers pledged to continue as long as the comet remained detectable. The legacy, 3I Atlas, forced astronomy to confront the diversity of interstellar objects. The first visitor, Oumuamua, was inert, showed no gas emission or dust, and had a highly elongated shape unlike any known comet or asteroid. The second, 2I Borisov, was an active comet, similar in many ways to solar system comets, but with a composition suggesting formation in a carbon monoxide-rich environment. 3I Atlas was active, showed strong outgassing and dust production, but had jets that defied explanation, a possible intrinsic magnetic field, an unusual composition with high nickel and carbon content, and a response to a CME impact that exceeded all predictions. The three objects sampled 3 different points in what was clearly a broad distribution of interstellar body types. Oumuamua represented one extreme, an inert, processed object that might have been a fragment of a larger body or a solid aggregate stripped of volatiles. Borisov represented something closer to standard comets, volatile-rich, and recently ejected from its parent system. 3I Atlas occupied a middle ground, or perhaps a completely different category, with properties suggesting both primitive and processed material, raising the possibility of hybrid bodies or unusual formation conditions. Dr. Amaya Moro-Martin at the Space Telescope Science Institute argued that the diversity was expected. Stars form from molecular clouds with a wide range of compositions, temperatures, and densities. The planetesimals and comets that form in these environments would reflect that diversity. Some systems might be carbon-rich, producing objects with high CO and organic content. Others might be oxygen-rich, favoring water, ice, and silicates. Some might undergo violent events, collisions, or close encounters that fragment and mix material from different zones. The interstellar population should be heterogeneous, and the 3 objects humanity had detected so far were just the beginning. The detection rate provided another constraint. 3 interstellar objects in 7 years, from 2017 to 2025, implied a steady flux passing through the inner solar system. Dr. Mauro Martin estimated that at any given time there were likely several interstellar objects within 1 AU of the Sun, but most would be too faint to detect until surveys improved. The Vera C. Rubin Observatory, scheduled to begin operations in 2025, would increase the detection rate dramatically, potentially finding dozens of interstellar visitors per year. Within a decade, the sample size could grow from 3 to hundreds, providing the statistical power needed to understand the population's properties and origins. 3I, Atlas, also highlighted the importance of rapid response. The object was discovered only weeks before perihelion, leaving little time for detailed pre-perihelion observations. The CME encounter, though fortuitous for science, was unplanned and nearly missed because of telescope scheduling constraints. Future interstellar detections would benefit from dedicated follow-up programs, automated alerts, and pre-allocated telescope time to ensure that critical phases of activity were not missed. The international coordination demonstrated during the 3I Atlas campaign provided a template for future efforts. The magnetic field evidence, though still debated, opened new lines of inquiry. If confirmed, it would be the first detection of an intrinsic field in a comet and would require rethinking comet interiors. The possibility that interstellar comets might include fragments of disrupted planets or planetesimals with metallic cores was not previously considered, but now had to be taken seriously. This had implications for planet formation theories, for the outcomes of planetary system evolution, and for the distribution of metals in the interstellar medium. The data from 3I Atlas would be analysed for years. The full dataset, including images, spectra, photometry, and astrometry from hundreds of observations, was being compiled into a public archive hosted by NASA's Planetary Data System and ESA's Planetary Science Archive. Researchers worldwide would have access, enabling independent analyses and new discoveries long after the comet itself had faded from view. The legacy of 3I Atlas was not just the observations made in 2025, but the questions it raised and the tools and collaborations it inspired for studying future visitors. The spectroscopic revelation, the aftermath of the CME, impact-delivered data that would consume the attention of spectroscopists for months. As 3I Atlas emerged from the plasma storm, instruments across multiple wavelengths captured something extraordinary. The comet's chemical signature had changed. The European Southern Observatory's X-shooter spectrograph, operating across ultraviolet through near-infrared bands, recorded emission lines that had either weakened dramatically or appeared for the first time since observations began in August. Dr. Paolo Lazzarin at the Padua Astronomical Observatory coordinated a rapid response spectroscopic campaign involving 14 facilities across 6 continents. The goal was simple but ambitious. Capture the comet's spectrum every 6 hours for 2 weeks following the impact, building a time-resolved chemical portrait of an interstellar object under extreme stress. The results challenged expectations at every turn. The most dramatic change appeared in the sodium doublet at 589 nanometers. Before the CME, sodium emission was barely detectable, hovering near the noise floor of even the most sensitive spectrographs. After November 20th, the D lines blazed with intensity, their flux increasing by a factor of 150 within 12 hours of first contact. Sodium atoms, normally bound in silicate minerals within dust grains, had been liberated either through thermal vaporization as grains heated in the CME's plasma environment, or through sputtering as high-energy ions bombarded the coma's dust population. The emission persisted far longer than thermal models predicted. If heating alone explained the sodium release, the emission should have decayed within 24 hours as grains cooled. Instead, observations through December 5th showed sodium lines remaining 40 times brighter than pre-impact levels. Dr. Lazarin's team proposed that the CME had fractured dust grains, exposing fresh surface area and allowing solar ultraviolet radiation to continue liberating sodium through photodesorption, a process where UV photons break chemical bonds and eject atoms from grain surfaces. Potassium emission told a parallel story. The resonance doublet at 766 and 770 nanometers, previously undetected, appeared on November 21st and remained visible for 9 days. The sodium to potassium ratio, measured at 28:1, fell within the range typical for carbonaceous chondrite meteorites, but significantly different from the 15:1 ratio common in ordinary chondrites, or the 50:1 ratio in cometary dust previously measured in solar system objects. This fingerprint suggested that 3I, Atlas's dust population, contained material chemically distinct from both asteroidal and cometary norms. Molecular emissions revealed their own transformations. The swan bands of C2, which had flared during the November 20th outburst, faded rapidly, but left behind an unusual residual signature. High-resolution spectroscopy from the Keck Observatory's HIAS instrument detected isotopic variants of the C2 molecule, specifically 13C12C and 13C13C, in ratios that deviated from solar system standards. The 12C, 13C ratio derived from these measurements was 78 plus or minus 6, significantly lower than the terrestrial value of 89 and even lower than most Oort cloud comets, which cluster around 85 to 95. This carbon isotopic anomaly pointed to formation in an environment where carbon isotope fractionation had proceeded differently than in the solar nebula. Dense molecular clouds, where temperatures remain below 20 Kelvin for millions of years, can produce such depletions through selective chemical reactions that favor heavier isotopes. The measurement provided one of the strongest pieces of evidence that 3I, Atlas's volatiles, formed in true interstellar space rather than in a protoplanetary disk around another star. The NH2 radical, a fragment of ammonia, showed unexpected behavior in the weeks following the impact. While most molecular emissions declined as the comet moved away from the Sun and activity waned, NH2 emission remained anomalously strong. Observations from the Apache Point Observatory's 3.5-meter telescope tracked the NH2 radical through early December, finding production rates that exceeded water production by a factor of 0.15, 3 times higher than typical cometary values. Ammonia is notoriously difficult to detect in comets because it exists primarily as a solid ice at cometary temperatures and sublimates less readily than water. The elevated NH2 suggested that ammonia ice was either unusually abundant in 3I, Atlas's nucleus, or that the CME impact had exposed deeply buried ammonia-rich layers. Ammonia abundance serves as another tracer of formation temperature. High ammonia content indicates condensation from a gas phase at temperatures below 80 Kelvin, conditions found in the outer regions of protoplanetary disks or in molecular cloud cores. Sulfur chemistry added yet another layer of complexity. The CS, carbon monosulfide molecule detected by ALMA in the millimeter range increased in abundance following the CME impact, but not uniformly. Maps of CS emission showed that it concentrated in a crescent-shaped region on the anti-sunward side of the nucleus, offset from the peak of water and CO emission. This spatial separation suggested that sulfur-bearing ices resided in distinct reservoirs within the nucleus, possibly in layers formed under different conditions or at different times in the comet's history. The spectroscopic data painted a picture of compositional heterogeneity within the nucleus. Rather than a uniform mixture of ices and dust, 3I Atlas appeared to be stratified, with different chemical zones revealed as the CME stripped away outer layers and triggered outgassing from previously dormant regions. Each emission line, each isotopic ratio, and each spatial distribution told part of the story of where and how this interstellar visitor formed, and each piece of evidence pointed away from simple explanations. The particle acceleration mystery. As spectroscopists documented chemical changes, high-energy astrophysicists were tracking something even more exotic. 3I Atlas was accelerating particles to relativistic speeds. The Fermi Gamma Ray Space Telescope, normally focused on distant cosmic sources, briefly turned its attention to the comet during the days following the CME impact. What it found defied conventional understanding of cometary physics. On November 22nd, Fermi's Large Area Telescope detected gamma-ray photons with energies between 100 million and 1 billion electron volts emanating from the comet's vicinity. The flux was faint, barely 3 sigma above background, but the timing was unmistakable, coinciding with the X-ray bursts detected by Chandra. Gamma rays at these energies are produced when electrons traveling near the speed of light collide with lower energy photons, boosting them to gamma ray wavelengths through a process called inverse Compton scattering. Dr. Reshmi Mukherjee at Barnard College led the analysis of the Fermi data. Her team calculated that to produce the observed gamma ray flux, electrons needed to be accelerated to energies exceeding 10 billion electron volts, equivalent to the energy of particles in terrestrial particle accelerators. The question was immediate and profound. What could accelerate particles to such extreme energies in the environment of a comet? The most likely mechanism was magnetic reconnection, the same process that powers solar flares and releases vast amounts of energy when oppositely directed magnetic field lines merge and snap. The CME's magnetic field, colliding with whatever intrinsic field the nucleus possessed, created reconnection sites, where magnetic energy converted into kinetic energy, flinging electrons and ions to high velocities. The efficiency required to match the Fermi observations demanded reconnection occurring at a rate and intensity rarely seen outside of solar flares or magnetospheric substorms on Earth. But reconnection alone didn't fully explain the observations. The gamma ray emission persisted intermittently for 18 hours after the initial detection, long after the densest part of the CME had passed. Dr. Mukherjee proposed that the comet's magnetic field, if it existed, was trapping accelerated particles in a miniature radiation belt. As particles bounced between magnetic mirror points near the nucleus, they would gradually lose energy through synchrotron radiation and inverse Compton scattering, producing the extended gamma-ray emission. Ground-based gamma-ray observatories attempted to confirm the detection using atmospheric Cherenkov telescopes, instruments that detect the faint flashes of blue light produced when gamma rays slam into Earth's atmosphere. The Veritas Array in Arizona and the HESS telescopes in Namibia both observed 3I Atlas during the predicted window, searching for photons with energies above 100 billion electron volts. Neither facility detected a significant signal, but the upper limits they established constrained the maximum energy of accelerated particles to below 50 billion electron volts. Cosmic ray detectors added an unexpected dimension to the story. The Pierre Auger Observatory in Argentina, designed to detect ultra-high energy cosmic rays from distant galaxies, noted a slight excess of air shower events in the direction of 3I, Atlas, during late November. The excess was marginal, only 2.1 sigma above background, and the cosmic ray energies were far too high, around 10-15 electron volts, to originate from the comet itself. Still, the correlation was intriguing enough to warrant further investigation. Dr. Alan Watson, at the University of Leeds, proposed a speculative scenario. If the nucleus possessed a strong magnetic field and the reconnection events were sufficiently violent, they might inject lower energy particles into the local interplanetary magnetic field. These particles would then be further accelerated by interacting with large-scale shockwaves in the solar wind, eventually reaching the ultra-high energies detected by cosmic ray observatories. The mechanism, called diffusive shock acceleration, is well established in supernova remnants and other astrophysical shocks, but applying it to a comet was unprecedented. Theoretical models of particle acceleration in cometary environments were sparse. Most previous work focused on the weak accelerations produced by the solar wind's interaction with cometary ionospheres, processes that produce particles with energies of a few thousand electron volts, sufficient to generate X-rays, but nowhere near the billion electron volt regime observed by Fermi. The 3I Atlas observations demanded new physics, or at least the application of physics previously confined to exotic astrophysical sources. Dr. Elena Amato at the Arcetri Astrophysical Observatory in Florence ran numerical simulations of magnetic reconnection in the comet's environment, incorporating parameters derived from the X-ray and radio observations. Her models showed that if the nucleus's magnetic field reached 300 to 400 nanoteslas near the surface and the CME compressed it to double that strength, reconnection could indeed accelerate electrons to multi-billion electron volt energies. The key requirement was a large-scale, coherent magnetic structure, precisely the kind of field expected from a metallic core with remnant magnetization. The particle acceleration data, though fragmentary and near the detection limits of multiple instruments, added a crucial piece to the 3I Atlas puzzle. Comets are not supposed to be particle accelerators. Their magnetic environments are too weak, their structures too diffuse. Yet there was evidence that this interstellar visitor had briefly transformed into a source of high-energy particles, generating phenomena more typically associated with stellar flares or pulsar magnetospheres than with icy wanderers from the depths of space. The rotation dynamics puzzle. The spin-up of 3I Atlas following the November 20th outburst raised questions that extended far beyond simple momentum transfer. As photometric data accumulated through December, astronomers noticed additional complexities in the comet's rotation that suggested its interior was not a simple, uniform mass but possessed structure that responded to torques in unexpected ways. Dr. Petr Šajrić at the Ondřejov Observatory in the Czech Republic specialized in asteroid light curve analysis, extracting rotation periods and shape information from brightness variations. When he turned his attention to 3I Atlas, the data refused to conform to standard models. The 15.87-hour rotation period, measured immediately after the outburst, remained stable through early December. But the amplitude of the brightness variations, the difference between maximum and minimum brightness, changed progressively. On November 23rd, the light curve amplitude was 0.38 magnitudes, indicating a moderately elongated or irregular nucleus. By December 8th, the amplitude had decreased to 0.31 magnitudes, suggesting the nucleus was becoming more spherical or that its orientation relative to Earth had changed. Schierick ruled out simple geometric effects through careful analysis of the viewing geometry, confirming that something physical was changing about how the nucleus scattered light. One possibility was that the outburst had modified the surface properties unevenly, creating new, bright or dark regions that altered the light curve shape as the nucleus rotated. Modeling this scenario required assumptions about where fresh ice had been exposed and where dust had been deposited, variables constrained only weakly by the spectroscopic data. The models could reproduce the observed amplitude change, but only if the surface modifications were concentrated in specific regions, covering about 15% of the total surface area. A more intriguing explanation came from considerations of the nucleus's internal structure. If the nucleus was differentiated, with a dense core surrounded by a lower density mantle, the outburst could have shifted material within the mantle, redistributing mass and changing the moment of inertia tensor. This is analogous to how ice skaters control their spin rate by extending or retracting their arms, though on a much slower timescale and driven by different forces. Dr. Schierick collaborated with Dr. Stephen Lowry at the University of Kent, an expert in the yaw effect, a subtle torque on small bodies caused by the uneven thermal re-radiation of absorbed sunlight. The yaw effect is typically studied in asteroids, where it can cause measurable spin rate changes over decades. For an active comet, the effect is overwhelmed by outgassing torques. But Lowry wondered whether thermal effects might still play a role in modifying the light curve. Lowry's thermal models showed that if the nucleus had regions of different thermal inertia, perhaps bare rock in some areas and fluffy ice in others, the temperature distribution would be asymmetric. As the nucleus rotated, different regions would heat and cool at different rates, creating thermal stresses that could subtly warp the surface. Over weeks, these stresses might alter surface topography enough to change the light curve amplitude by the observed amount. High-cadence photometry from amateur observers proved invaluable in constraining these models. The global network of backyard astronomers captured light curves with time resolution as fine as 30 seconds, revealing micro-variations that professional surveys, with their wider fields and longer exposure times, missed. These micro-variations, periodic fluctuations with amplitudes of 0.01 to 0.02 magnitudes and periods of 2 to 4 hours, suggested that localized jets were turning on and off as active regions rotated into and out of sunlight. The jet activity's influence on rotation was quantifiable. Dr. Yaeji Kim at Seoul National University used the jet morphology observed in amateur images to estimate the torque each jet exerted on the nucleus. By summing the torques from all visible jets and accounting for their changing orientations throughout the rotation cycle, Kim calculated the net angular momentum transfer. Her results showed that while the major jets produced substantial torque, they partially cancelled each other due to their roughly symmetric distribution around the nucleus. The net torque from the jets, accounting for cancellation, was approximately 3 times 10, 8 Newton meters, enough to change the rotation period by about 10 minutes over the course of the outburst, matching the observations. But Kim's analysis also revealed that the torque vector was not perfectly aligned with the rotation axis. Instead, it was tilted by about 15 degrees, meaning the outburst not only sped up the rotation, but also slightly altered the orientation of the spin axis. Spin axis precession, the slow wobbling of the rotation axis, like a tilted spinning top, normally occurs on timescales of years or decades for small bodies. But the intense torques from the November 20th outburst could have induced a measurable precession over weeks. If confirmed, this would manifest as a gradual shift in the viewing geometry of the nucleus, potentially explaining the light curve amplitude changes without requiring surface modifications or internal mass redistribution. Testing this hypothesis required observations spanning months, extending well beyond the favourable observing window when 3I Atlas was bright enough for detailed photometry. Dr. Sherrick organised a long-term monitoring campaign, coordinating observations from professional facilities and amateur networks to capture at least one full light curve per week through mid-2026. The goal was to track how both the rotation period and light curve shape evolved, providing constraints on the nucleus's internal structure and the extent of spin axis precession. The rotation dynamics of 3I Atlas offered a window into its interior that complemented spectroscopic and magnetic data. Each torque, each period change, and each light curve variation carried information about mass distribution, surface properties, and structural integrity for a body that remained unresolved in even the highest resolution images. These indirect probes were the only tools available to peer beneath the surface and understand what this interstellar visitor was made of and how it was put together. The dust production paradox. While attention focused on gas emissions and magnetic fields, dust, the solid component of cometary activity, told its own puzzling story. The amount of dust 3I Atlas produced, how it evolved after the CME impact, and how its properties compared to solar system comets all pointed to peculiarities that deepened, rather than resolved, the mystery of the comet's origin. Dr. Matthew Knight at the U.S. Naval Academy had spent decades studying cometary dust, developing techniques to measure dust production rates from scattered sunlight. When he analysed 3I Atlas, the numbers didn't add up. The dust-to-gas mass ratio, derived by comparing scattered light in the continuum to gas emission line strengths, measured 0.12 inches early December, lower than the typical cometary value of 0.5 to 2. This meant 3I Atlas was producing far more gas relative to dust than expected. Gas-rich, dust-poor behaviour is occasionally seen in solar system comets, particularly those making their first approach to the Sun and sublimating highly volatile ices like CO and CO2. But 3I Atlas was receding from the Sun when these measurements were made, at a distance of 1.4 AU, where water ice drives most activity in typical comets. The persistent high gas production with relatively little dust suggested that the nucleus's ice was either unusually pure or that the dust grains were so small they didn't scatter much visible light. Size distribution analysis provided crucial insights. Dr. Knight used polarimetry data from Calar Alto Observatory combined with multi-wavelength photometry spanning ultraviolet through near-infrared to constrain the dust grain size distribution. The standard approach fits power law size distributions to the observed scattering properties, deriving parameters that describe how many grains exist at each size. The best fit model showed a steep power law with an index of -3.8, indicating that small grains vastly outnumbered large ones, even more so than in typical comets. The distribution peaked at radii around 0.3 micrometers, with relatively few grains larger than 10 micrometers. Such small particles have high surface area to mass ratios, making them susceptible to radiation pressure and easily carried away from the nucleus by gas drag. This explained the low dust-to-gas ratio. Most of the dust mass was in tiny grains that contributed little to the scattered light measured in visible wavelengths. But why would 3I, Atlas, produce preferentially small dust? One possibility was that its dust consisted of fluffy aggregates, loosely bound collections of tiny monomers held together by van der Waals forces. When released into the coma, these aggregates could fragment easily, breaking into their constituent submicrometer particles. Solar system comets show evidence of aggregate fragmentation, but the efficiency in 3I, Atlas, seemed extreme. Dr. Arika Higuchi at the University of Occupational and Environmental Health in Japan proposed an alternative: electrostatic disruption. In the coma's partially ionized environment, dust grains acquire electric charges through photoelectric emission when solar UV light ejects electrons from grain surfaces. If grains in 3I, Atlas's coma, charged more efficiently than usual, perhaps due to their composition or the enhanced UV flux during the CME interaction, the electrostatic repulsion between charged grains could overcome cohesive forces, shattering aggregates into fragments. Higuchi calculated that for typical grain compositions and solar UV intensities, electrostatic disruption becomes important only for very small aggregates, a few micrometers or less. But if the CME delivered additional ionizing radiation through its enhanced UV and X-ray flux, or if the dust grains had unusually low work functions, the energy needed to eject electrons, then even larger aggregates could be disrupted. This mechanism could explain the sudden increase in small grain production following the CME impact. Compositional clues from infrared spectroscopy added another dimension. The Spitzer Space Telescope's observations in the 10 micrometer silicate feature showed an unusually weak and broad emission band compared to typical cometary dust. Silicates produce characteristic spectral features whose shapes depend on their crystalline structure and chemical composition. Crystalline silicates minerals with ordered atomic arrangements produce sharp, narrow features, while amorphous silicates, glassy materials with disordered structures, produce broad, smooth features. 3I, Atlas's weak, smooth 10 micrometer feature, suggested its silicate dust was highly amorphous, indicating formation in a low-temperature environment where crystalline minerals could not form. This was consistent with interstellar origin, as dust in molecular clouds consists predominantly of amorphous silicates. But the weakness of the feature relative to the continuum emission indicated that silicates made up a smaller fraction of the total dust mass than in most comets. What comprised the rest of the dust? Carbonaceous material organic compounds, and amorphous carbon scatter light relatively uniformly across visible and near-infrared wavelengths without producing strong spectral features. If 3I, Atlas's dust, was carbon-rich, the flat continuum and weak silicate features would be natural consequences. This aligned with the high CO abundance and the elevated carbon-bearing molecules detected spectroscopically, painting a picture of a nucleus unusually enriched in carbon-bearing materials. The dust trail left behind the comet provided additional information. As 3I Atlas moved through space, dust grains ejected from the nucleus gradually separated based on size, with larger particles less affected by radiation pressure lagging behind the nucleus, while smaller particles were pushed ahead. Over weeks, this size-dependent separation created a trail of dust stretching along the orbital path. Infrared observations from NEOWISE detected 3I, Atlas's dust trail, extending approximately 500,000 kilometers behind the nucleus by early December. The trail's brightness and thermal emission characteristics indicated it contained primarily larger grains, hundreds of micrometers in radius, that had been ejected weeks earlier during the perihelion passage. These large grains carried significant mass, but contributed little to the visible brightness of the coma, hidden by the overwhelming scattered light from countless tiny grains. The dust production paradox, high gas, low dust, unusually small grains, and weak silicate features all pointed toward a nucleus with properties diverging from solar system norms. Whether these differences reflected an exotic formation environment, unusual composition, or processes that occurred during the long interstellar journey remained ambiguous. What was clear was that 3I, Atlas, was not just another icy body following standard comet physics. Its dust, like its gas, jets, and magnetic field, demanded explanations that stretched beyond conventional models. The amateur revolution in cometary science. The 3I Atlas campaign marked a turning point in how science approaches transient celestial events. While multi-million-dollar spacecraft delivered data on hydrogen envelopes and gamma rays, the most comprehensive portrait of the comet's visible structure emerged from a distributed network of amateur astronomers working with equipment they bought, built, or borrowed. The revolution began quietly in online forums and Facebook groups dedicated to astrophotography. When professional observatories announced 3I, Atlas's discovery, in August 2025, amateur astronomers immediately began planning observing campaigns. By September, coordinated imaging sessions were underway across 6 continents, with observers in complementary time zones ensuring nearly continuous coverage as the comet rotated and evolved. The tools of modern amateur astronomy would astound observers from even 2 decades ago. Cooled CCD and CMOS cameras with quantum efficiencies exceeding 80% capture photons, with an efficiency rivaling professional instruments. Commercially available telescopes with 12 to 16-inch apertures and adaptive optics systems deliver image quality that approaches the diffraction limit. Software for image stacking, calibration, and photometric analysis runs on standard desktop computers, automating processes that once required specialized expertise. Gerald Riemann, an amateur astronomer based in Namibia, captured some of the sharpest images of 3I, Atlas, using a 12-inch astrograph and a monochrome CMOS camera. His images from November 15th resolved 4 distinct jets radiating from the coma, each visible as narrow streamers extending 200,000 to 300,000 kilometers from the nucleus. By comparing images taken hours apart, Riemann tracked how the jet's orientations changed with the nucleus's rotation, providing real-time confirmation of the 16-hour period measured from light curves. What made Riemann's contribution particularly valuable was his willingness to share raw data. Rather than posting only processed images, he uploaded FITS files, the standard astronomical data format, to public servers where professional astronomers could download and analyze them. Within days, researchers at multiple institutions were using Riemann's amateur data alongside official observations from Hubble and other facilities, treating both sources as equally valid. Michael Jaeger in Austria brought a different expertise: time-lapse imaging, showing the comet's evolution over hours and days. His sequences, captured every 15 minutes throughout the night on November 19 to 20, documented the CME impact's visual effects in real time. The sequences showed the coma brightening abruptly, the tail disconnection event, and the emergence of the new jet that professional spectroscopy would later identify as a co-rich outflow. Jaeger's animations circulated rapidly through social media, reaching millions of viewers and demonstrating that cutting-edge science wasn't confined to ivory towers or mission control rooms. The images appeared in news articles, NASA press releases, and academic presentations, acknowledged as equal contributors to the scientific record. For Jaeger and hundreds of other amateur contributors, This recognition represented a validation of the amateur astronomy community's technical capabilities and scientific rigor. The distributed network model proved resilient to the challenges that plague single-site observations. Weather, technical failures, and scheduling conflicts that might prevent a professional observatory from capturing critical data were mitigated by redundancy. When clouds covered Chile's observatories during the peak of the outburst, observers in Australia and South Africa captured the event. When a camera failure affected one amateur's system, a dozen others provided backup coverage. Coordination happened through platforms designed for collaboration. The Comet Observation Database, a public repository managed by amateur astronomers, collected light curves, astrometry, and image metadata from contributors worldwide. Automated algorithms checked for consistency, flagging outliers, and ensuring data quality. By December, the database contained over 15,000 measurements from 300 observers, a dataset rivaling professional surveys in scope and surpassing them in temporal coverage. Professional astronomers increasingly acknowledged the amateurs' contributions, not just politely, but substantively. Dr. Matthew Knight co-authored papers with amateur contributors, crediting them formally in the author list rather than relegating them to acknowledgements. Dr. Nalin Samarasinghe at the Planetary Science Institute invited amateur imagers to participate in observing programs, integrating their data streams with professional observations. The technical quality of amateur contributions varied, but the best images matched or exceeded those from billion-dollar spacecraft. Part of this success stemmed from favorable geometry. Ground-based observers viewed 3I, Atlas, at phase angles and distances where the comet's jets were most visible, while space telescopes struggled with the bright coma overwhelming their detectors. But technique mattered too. Amateur astronomers developed specialized processing workflows optimized for cometry features, stacking dozens of short exposures to suppress noise while preserving sharp detail in the jets. The success of the 3I Atlas amateur campaign prompted discussions about formalizing these collaborations. The International Astronomical Union's Working Group on Comets considered establishing official channels for amateur data submission, with peer review processes ensuring quality while respecting the independence of amateur networks. NASA and ESA explored partnerships where mission planning incorporated amateur observations, using their continuous monitoring to guide spacecraft targeting and optimize observation windows. For the participants, the motivation transcended scientific credit. Many amateur contributors described a sense of connection contributing to humanity's understanding of a visitor from another star system, participating in discovery rather than passively consuming it. The images they captured weren't just pretty pictures, but scientific data that helped professionals interpret spacecraft observations and test theoretical models. This democratization of science, enabled by technology and organized through digital networks, represented a model applicable beyond astronomy. Citizen science projects in fields from biology to climatology were demonstrating that distributed participation could tackle problems. Traditional science struggled with problems requiring constant monitoring, rapid response, or coverage spanning the globe. 3I, Atlas, showed what was possible when experts and amateurs collaborated as equals, each bringing complementary strengths to a shared challenge. As 3I, Atlas faded from view through late December and into 2026, the amateur community remained engaged, continuing to capture images as the comet dimmed beyond naked eye visibility. Their observations would document the long fade, track any unexpected outbursts, and provide the baseline data against which future interstellar visitors would be compared. The revolution they sparked, proving that anyone with dedication and decent equipment could contribute meaningfully to frontier science would outlast any single object, transforming how astronomy approached rare and transient phenomena.